today is engineer Chow Chee Meng. He's actually a local geotechnical consultant. Yeah, he has been in the business for quite a while. He's actually a director of G&P. Yeah, I'm sure all of you lah, if not most of you, know what G&P is lah. G&P Geotechnics. This is how many years? I'm not sure, but quite a long established company started by Dr. Gui lah. Dr. Gui.
Yes.
Used to be called Gui and Partners. Now they changed it to G&P. And Engineer Chow is one of the directors lah for G&P Geotechnics. Engineer Chow is a graduate of University of Malaya, Bachelor of Engineering in Civil Engineering. What year was that? Not the year was
2001.
Oh, 2001. Oh, so there's 20 plus years already. So he has been with the company for quite a while. In fact, he also left the company for a short while. And if I remember correctly, he was in Kazakhstan, one time Kazakhstan, doing an interesting project. And in fact, he presented a paper in one of our previous GSM forums.
Yeah, very good memory, Professor.
Yeah. It's quite a while already. Yeah. So that was an interesting project. And anyway, he's back in G&P, and he was involved in many award-winning projects, quite a long list. And he has also won some awards for publication. In IEM, they give out awards for publications, as well as awards for those the best project for that year or something. And of course, Engineer Chow has been very active in the Institution of Engineers Malaysia, IEM, and also the Board of Engineers Malaysia, VM. So with that brief introduction, now I pass the floor to you, Engineer Chow. You can start your talk.
Yep.
Okay. Yeah.
Thank you, Professor Tan, for the kind introduction. So I'm happy today that to meet Professor Tan Boon Kong again. Many years back, we used to meet more often in IEM activities and things like that. So it's good to see Prof Tan still active and still very enthusiastic in organizing talks for everyone. Okay. So everyone, Prof, just to check again. Now I'm using the presentation mode. Can everyone see my screen?
Yeah.
Can you see my screen?
Yeah,
okay.
Very clear. Yeah.
All right. Okay, so the title of my presentation today is Foundation Challenges at Geological Interface Zone. Just to give a quick recap, I have actually presented this same set of materials sometime on 16 May 2023 for Malaysian Geotechnical Society. And then Professor Tan asked me whether I can repeat it for GSM. So, and therefore, this is where am I today. So my presentation is from the perspective of from an engineer, okay, because of course my experience, my training, etc. is on geotechnical engineering. On the geological aspects, mainly I'm based on the observations and the information that I've obtained. Maybe some of you here would be able to give me more insights with regards to some of the informations that I'll be sharing here today. Okay, let's go straight to the topic at hand. So a quick introduction. Basically, geotechnical challenges at interface zone have been reported previously. I mean, for example, by Mitchell in 1985 in a paper that he published for Southeast Asia Geotechnical Conference. He discussed about the challenges that his team faced in the design for the foundations for the Pan Pacific Hotel on Pinnacle and Cavernous Limestone. Those are you, I believe most of us are familiar with this structure. This is near the UMNO building, somewhere in Chow Kit. So previously it was known as the Pan Pacific Hotel. And of course, Professor Tan also, from listening to Professor Tan's talk and his paper, this is where I have I'm more alert to some of the potential issues and challenges at geological interface zone. So in 2004, in the Malaysia Geological Conference, I think Professor Tan, he summarized some of the cases which he have encountered. So in a paper titled "The Practice of Engineering Geology in Malaysia." So I believe something that we Malaysian engineers or geologists that have I think we should be proud of is that we have been addressing the challenges associated with limestone formation, and this has been widely discussed in conferences in whether in Malaysia or even overseas by Malaysian engineers and geologists. So normally, for those who are not familiar, engineers from other countries which are not familiar with limestone formation, usually they are very, very worried about works, geotechnical works or geological works in limestone formation. But the good thing about for Malaysian is that we are quite... Sorry, I'm seeing some messages. Never mind, I'll just ignore the message. So there are some challenges. So as I was saying, foreign engineers, they are usually quite worried if they have not done any works in limestone before. So, but we Malaysians, especially in KL area or Ipoh or even Langkawi areas, I think we understand the challenges, and I'm proud to say that most of the time we have developed good skills in that. So these have been widely discussed. But where we have the special conditions where the limestone interfaces with granite, this will further complicates the ground conditions. As I will share later on, what I meant by further complicates the ground conditions. And of course, I quote directly from Professor Tan's paper in 2004. He mentioned that in fact, at granite limestone contact zone, it often produces a deep trench due to differential solutioning of limestone along the contact zone. To give you an example, this is the Pan Pacific hotel that I mentioned earlier. You can see from here, as you follow my cursor here, you can see that this is the outline of the final 25-story bedroom tower scheme. In fact, they have to make changes to the layout and orientation of the building. You see, the original building, the design actually requires a 14 and 19-story bedroom tower, which is arranged different. You see, this is the original arrangement of the hotel tower. But here you can see this line here, based on the SI information, this is the interpreted approximately edge of the cliff, where there is a very obvious difference in the depth of the limestone. But towards the top of this line, actually it's shallow. The term is shallow, where it's less than 100 feet. That means it's less than 30 meters, about 30 meters. Whereas the moment it crosses this line, it's actually very, very deep. The limestone is more than 300 meters. So the original building as such actually gives some challenge, which is very costly to overcome if the building is being positioned as such, where you have big settlement at the area where you have very deep piles. Of course, then you have much lesser settlement at the area with shallow bedrock. And on top of that, at that time in 1985, in the 1980s, even now, I believe, it's very difficult to form the piles at depth, which is very, very deep. As you have seen later on, some of the piles here actually goes far deeper than, in fact, 30 meters. So they have to use barrette piles at that time. So you imagine if the majority of the piles require barrette, of course, you may not make the project viable, even by today's standard, let alone in the 1980s. Here is the cross section. I mean, here, as you can see that they have indicated the hotel tower. This is the tower outline. From all the boreholes, you can see that the construction level is about 100 plus 100 feet. So you see, after this edge of this is a so-called shallow area where it's about less than 30 feet. Sorry, less than, in this case, less than 30 feet. But the moment it crosses here, it gets deeper. Here, you see, it's about minus 100 feet. So plus here is already about 200 feet. So 200 feet is close to 60 meters. And if you go further down, it's even worse. Yeah, it goes down to minus 240 feet plus another 100 is about 300 over feet. That means the depth to the limestone is easily about 90 to 100 meters. So you can imagine the drastic change in the limestone bedrock and the interface zone. So the strategies that was adopted at that time is that the designer decided to carry out a study on the performance of the piles. Basically, they're divided into two zones, where you have the shallow pile, which is less than 30 meters deep, and therefore they design it with 1.5 meter rock socket into limestone. Whereas for the deep pile, which is on average about 75 meters deep, as I've shown you here, they required to use barrette, because barrette, the construction of barrette piles is that, for those who are familiar with ball pile construction, ball pile in Malaysia, the popular method is using the rotary drilling using a calibar. So there's limitation in terms of how deep the calibar can go. So whereas for diaphragm wall, they are using the line leader. So in terms of depth, it provides better in terms of achievable depth that can be constructed. So at that time, of course, the final layout, they have to use a combination of ball pile at the shallow, so-called shallow bedrock zone, whereas at the deep area, they have to use the barrette piles. So you imagine again the challenges. So if you are not aware of it, then during construction, you can imagine the headache, the potential problem, the time delay, and the overrun, etc. Okay, this diagram I've taken from the paper by Professor Tan. Again, you can see from here. Maybe Professor Tan later on he can share a little bit more information, because you can see from here at this area, this on the left-hand side of this diagram, the borehole mainly show granite. And you can see this contour actually shows the depth of the granite bedrock, ranges from 6 meter to 14 meter. And then at limestone area, of course, it's deeper. But the interesting part is that there don't seem to be any information at the contact zone. So I'm a bit curious on that, on this particular approach. Probably, my guess is at that time, the design has decided to avoid the contact zone because of the uncertainties with the behavior of the soil. So the SI is concentrated at the granite zone or the limestone zone. Anyway, just to put into perspective, you can see that on the left-hand side of the plan just now, you can see the granite bedrock depth. Actually, it goes deeper and deeper as it goes towards the contact zone. You can see again, the limestone level also quite shallow, but at the contact zone, it's suspected that the level will be very deep because of the differential solutioning that I mentioned earlier. Anyway, we don't have information here, of course, but from the understanding of geology, I think the possibility is very high that the bedrock here tends to be deeper, etc. So from the two simple papers that I referred to in this introduction, I just want to set the tone in terms of what the main message that I want to convey to my fellow practitioners in the field of geotechnical engineering or geological works. At geological interface zone, of course, we have to be extra careful on the ground conditions. Just to elaborate further, what I meant is basically we cannot do it like business as usual based on our normal practice. At those areas, we have to put more thoughts into it, and the investigation, the planning and the scope of the subsurface investigation, even though it's a very simple tool, it becomes very important because it allows us to actually plan ahead and try to mitigate the risk and the challenges ahead, rather than giving us surprises, unpleasant surprises during construction. Okay, now I move into actual case history from my own projects. In this presentation here today, I'll be sharing two case history. One is at the case history one is on granite and limestone interface zone. I'm sharing with you what are the observations that we obtained from the SI information, and how from the engineering point of view we address the situation, and how to make sure that the foundation is adequate and achieves the intended purpose of supporting the structure and the architectural intent of the development. So for those who may want to have further readings and find out more about these particular details about these particular challenges, actually the materials that I'm presenting here, I published in a paper in 2019 for the 16th Asian Regional Conference in Soil Mechanics, on Soil Mechanics and Geotechnical Engineering in Taipei, Taiwan, with my colleague So and Li Ying. So the paper, I think, should be easily accessible either from my company website or maybe on the internet. Anyway, if those who are interested, I'm sure maybe you can communicate with Professor Tan. I'll be more than happy to share for those who are interested. So again, just to give a perspective, a quick overview, a macro view of where is the site location. This site is actually, as you can see from the geological map that we get from JMG, the project site appears to show that it is in a granite formation, whereas not too far away, it's supposed to be limestone. Okay, but from here, one would thought that, oh, okay, it's not really at the interface, but I'm sure all of us are aware that the boundaries of all these limestone or granite are quite approximate based on the information given to JMG throughout the years. So this, to me, this is close enough for me to warrant a more detailed study whether there is some issues at the interface zone that I've discussed earlier. So like I mentioned in the introduction, we are quite well aware of what are the problems in typical limestone bedrock. I mean, we are very worried about features such as overhang, pinnacle, floaters, cavity, collapse cavity, and etc. So there are many discussions about this already. So if you have an interface zone, you have to cater for limestone at the same time the interface zone. And for works in limestone, especially when we want to describe about the condition, the classification of the cast, the degree of cast for the limestone, for myself, I rely on this classification. Basically, something like they use the word something related to the age of the cast. If you're talking about juvenile cast, then you will have less adverse features. As the terms goes towards more older cast, youthful cast, then you have more such features like stream sink, sinkholes. Mature cast, of course, it gets more complicated. The category that we describe is cast K3. I'm sure again from my geological cousins here, I think they are very familiar with this. I would think that they will know. They will use this description much more often than myself. Of course, if you have complex casts, you have all these kind of issues which are quite common in Malaysia. Of course, extreme casts, basically you have all the different types of challenges associated with adverse features of casts. Okay, for this particular site, actually it's in PJ near Kanajaya area. We were very lucky that we have very supportive client. The client came from an engineering background, and he understood the importance of SI. And this particular client is not the type that save on SI. And the moment we highlighted to them that there is a potential issue related to the ground conditions here. In fact, they asked us to carry out as much boreholes as possible because they knew that if you carry out more boreholes, you actually reduce potential problems during construction, and which is true enough. I mean, I must admit that from all the information that we have obtained from here, I think the construction works able to proceed relatively smooth despite a very complicated site. What I mean by a very complicated site from a geological and technical point of view is that from the total of 161 numbers of boreholes carried out, I mean, I flipped through it. This one, you can see from here what kind we have a very jumbled and complicated geological conditions at this interface zone. What we have divided it into, you see the top right hand box is mainly the Tower A area. The Tower A area, mostly we color coded it green from the borehole information, mostly are granite, Tower A. Of course, we have some with some mixture of limestone as well, labeled pink color, limestone and granite. And then at the car park podium area, you can see from here also, mostly is still granite, but because at the interface zone, we have different type of materials. We have skarn and some other metamorphized material at the interface zone, but it's still mostly granite. But then when it comes to Tower B, you can see based on the colors that I've shown here, we have far more limestone at the Tower B area. So, I mean, for me, even this kind of situation is not something that I will encounter in my everyday, I mean, most of my projects since my graduation, 20 over years already, I think I only encountered such situation like 2 or 3 times throughout 20 plus years working. So what I meant by that, just to show you from the bore logs, this is how my company, we summarize the bore logs information. Basically, just to give you a quick overview, we plot it to the existing ground level. And this legend here, it shows the SPTN values. And here is the major and minor component of the soil. So you can see at the granite zone, it's nothing really too different from some of the projects that we encounter in granite zone, that you have SPTN gradually increases with depth. And then the green color is the type granite rock which we encounter from the boreholes. And the bedrock level is typically about 40 to 50 meters below ground level. So you can see from here, very interestingly at this area, in fact, just some of the boreholes at the top there, just before encountering granite, we have some schists just before that. So again, I do not know the real reasoning. Again, maybe the geological experts here will be able to shed some lights on this. But from the observation here, there's a very clear trend that these are the occurrences that we have encountered. Now, the interesting part is that at the limestone granite zone, you can see here, what we have shown here is that red color is the limestone. Okay, if you look at the plan there just now, so it's not consistent in all the boreholes. Some of the boreholes have it. These are an extract of some of the boreholes where we encounter limestone floaters. And the challenges here is that, first of all, you can see that the level where the limestone floaters detected varies. Some is as shallow, about 20 meters below ground, we encounter it. Some is deeper, about 40 meters below ground, we only encountered the floaters, 20 to 35, 35 to 40 meters. And the thickness also varies. Okay, some are quite relatively thinner, maybe you're talking about close to 2 to 3 meters, but some are as thick as 20 meters. And the problem with this interface zone from a foundation point of view is that we do not know how widespread is this thickness. And secondly, after the limestone, we core through the limestone, you can see that the soil beneath it, there is a considerable thickness of soil beneath it. I mean, this is close to This is definitely more than 5 meters, close to 10 meters. This is definitely more than 10 meters. The SPTN values actually is quite low. I mean, in this case, is 7, 11, and 14. This one is typically less than 20, in the region of 16 to 20 something. So you imagine if the foundation sits somewhere on this floater and with the load from the high-rise building, this layer of soil will compress, and this may cause this. Not just may, I think it will cause problems in terms of differential settlements to the building performance. So these are the challenges. And the good thing from the extensive SI carried out is that we can start make plannings on how to design the foundation and how to tackle this problem. So again, for this particular site, because of the interface zone, we have different types of besides granite and limestone, we have different types of minerals and skarn that we have encountered. Here we have wollastonite. This according to our geologists. We also encountered some pyrite, foolscole, and we have some breccia as well, the interface zone. So we have all different types of rocks and minerals. So one of the challenges that we have to overcome is that from the geotechnical engineering point of view is that because there's a big numbers of floaters which vary in thickness and the extent, the nature, and etc. The piles are designed to socket into competent granite bedrock. That means we do not want a situation where some of the piles will go to granite bedrock, some sit on the floater, you have different settlement. The strategy is to bore through the limestone. So of course the result from the SI is very convincing. Again, this is a value from the SI. The result from the SI is very convincing, and we as the project also be able to work out what will be the cost impact to the foundation. And despite this, the project is still viable, and I think it's very successful because phase one of these 2 towers are completed, and they are launching the new phase again as well. All right. So once we agreed on the approach towards the design of the foundation, of course we wanted to verify the performance of it, our assumptions, whether it's valid or not. So you see, the design parameters that we adopted, we include the shaft friction in soil, 2 times FCN value. The shaft friction in granite, we based on 1,500 ultimate value. This is based on our experience for bore pile in granite formation with minimum unconfined compressive strength of 40 megapascal. We usually limit the end bearing to about 15% of pile working load to limit the risk of, because the end bearing for bore pile, it depends very much on the contractor's workmanship. If the contractor is willing to clean the bottom of the bore pile better, the end bearing can be very high. But because of the constraint in terms of time, the productivity, so that's why we have to make a judgment in terms of limiting the end bearing to a certain percentage that is low enough, even when they don't achieve it, the foundation will still be safe. Okay, but of course we want it to be economical design at the same time. Another tools that we have used quite regularly to determine where is the competent bedrock is. Just to give a bit of a historical perspective, I mean, many years back, how the supervisors, how the construction of bore pile rock socket is verified is actually based on the supervisor's experience. That means if you feel that the rock is sound enough based on how difficult the machine core through the rock, the sound of the coring, then he will accept it. So as you can imagine, there's a lot of subjectivity on that, a lot of arguments, contractual arguments, etc. So we try to reduce it. Of course, the system is not perfect. We try to reduce such an argument. We actually make use of the tools of point load test. So we use the point load test on minimum 3 rock core samples retrieved during bore pile construction, and make sure that it achieves the minimum index strength of 3 megapascal. I highlight here that this is site specific. That means doesn't mean that all site is the index strength of 3 megapascal is defined as the solid rock. This one we also carry out point load tests for the during the SI as well. So we established that most of the competent rock here, they actually can achieve point load strength of 3 megapascal. However, I mean, we have to cater for some uncertainties at site as well. What if some of the rock are slightly weathered? Okay, it's not fresh rock, but it's slightly weathered. You may have IS which is less than 3 megapascal. So what we do is that we actually reduce the friction for those material, and we give a tabulation of equivalent rock socket length for every 1 meter of partial rock coring length, based on the recommendation that I published with my co-author, Dr. Tan, in 2013. This is the paper that we have published it. Foundation Design, Construction and Limestone Formation, a Malaysian consultant's experience in a symposium in Singapore in 2013. What we mean by that is that if you look at this table, when you work backwards, in other words, if you obtain the point load strength of more than 3 for the particular rock when you are drilling through it, that means that particular layer can be considered as 100% rock socket. That means the friction is about 1500 kPa. But if you get something less than 3, let's say 2 to 3, we actually downgrade the friction to 900 and so on, 600, 300. Of course, if any less than 0.5, it's no longer considered as rock socket. It's basically based on soil. So if let's say you encountered all the materials less than 3, doesn't mean that those are not considered as rock socket, but it's not full rock socket. That means it's equivalent to 60% of it only. So in that case, let's say the original design is 3 meter, then in this case, they have to lengthen it by more than 3 meter. That means it's probably close to about 4 meter. Let's say 3 divided by 0.6, it's close to 5 meters. But we make note to the contractor, because this material are supposedly of lesser strength, they will only get paid based on the original 3 meter, even though they may be drilling 5 meter, but they only still get paid 3 meter. This is very important because otherwise, you will not be able to control the quantities with certainties during construction, and there will be a lot of VO, etc. But the important thing is that this is communicated clear and early to all the tenderers so that they know what they are pricing for. So from the instrumental test results, we have 2 numbers of printing test files to verify our assumptions, design assumption. We have pile diameter of 900. 900 because small diameter, we use traditional cartilage blocks, whereas for the bigger diameter, 1.8 meter diameter, we use the bidirectional test results. This shows typical instrumentation. We always do the instrumentation with string gauges, telltale to monitor the settlement and the mobilized capacity. So similar set of instruments, type of instruments, string gauge. The difference here is that we have the hydraulic jack for bidirectional tests, because this one, the test load will be very high. Bidirectional will be more practical. In fact, I don't think it's safe to use cartilage for such large pile diameter and large test load. So this is the typical results that we have obtained. Of course, this shows the level of the string gauges. As you go deeper, you can see that at the rock there, this one gets about 900. Soil is close to about 100 kPa or 10 ton per meter square. End bearing for 900, they achieve about a 35 millimeter settlement. This is what I meant, you see. End bearing for ball pile, usually they require quite large settlement before they mobilize the end bearing. This one settles about 35 mm and mobilize about 3000 kPa. For the bigger pile diameter, bidirectional, you can see that the rock shaft better, 1004, close to 1004. Soils about 150 to 200. The same thing, because we have 2 portions of the instruments. The rock below the hydraulic jack also reaches about 1300 to 1400 of rock friction. And here, for this particular pile, 1800, you can see that it achieved much better end bearing. It can go as high as, close to 7,000. This is 700 ton per meter square. That means 7,000 kPa. So it reaches during the 3rd loading cycle. As a summary, you can see from here, the design assumption is that we assume the soil friction about 2 times SPTN. From the test pile, we get about 5 to 1.5 N. Green looks like higher, red looks lower. And then the shaft friction in rock, this is in granite. It seems that from both the test pile result, it seems like the achievable ultimate capacity is lower than the assumptions. But I will explain later on that this is not entirely true. Whereas, as I explained earlier, on end bearing, because of uncertainties in the workmanship, you can see that the range can vary quite widely, from as low as 1,900 for this particular pile, 900 diameter pile, to as high as 6,750 for a bigger diameter pile. One thing that we can observe is that for TP200, you can see that the soil friction is much higher, but we don't believe that this is true because we notice there's slight pile bulging on the top portion of the test pile, which may have contributed to the exceptionally high value of shaft friction. Despite this, later on I will explain, both the test pile results here show that the design parameters assumed is well presented to the ground condition when we adjust it based on site obtained IS value. What I meant by that is that if you recall earlier, when our design is based on, if you encountered all the point load strength of more than 3 megapascal adjusted for the 50 millimeters diameter size, then the assumption is about that it should achieve about 1,500 kPa of friction. But if you have more weathered materials, then the assumption is that you should reduce the frictional capacity of the rock as well. And this is what happened. You can see from the 900 diameter piles, in fact, for the upper layer, the point load, we know that we get about 900, close to 900 kPa of shaft friction. And if I divide 900 to 1,005, that means the ratio is about 0.6. And therefore, if you see, if I divide my calculated equivalent rock socket length, the 1.47, I divided by the 2 meter here, actually I get 0.7. So if we use a method where we adjust the rock socket, that means we will be getting very similar performance. That means it's in order. And if you look at the other pile, why the friction is higher, in fact, the IS value consistently is quite high, from more than 4 to about 8. And that's why we get frictional value of much higher, close to 1,004. And this is about if you talk about the actual equivalent rock socket length, it ranges typically about 0.9 and matches closely with what we will have assumed as 1. That's why the summary is that the approach that we have adopted, which is based on equivalent rock socket length, works well because the shaft friction tallies with the point load test results with some correlations on the recovered rock during bore piling works. I think this is a very important message. So the conclusion, for a simple conclusion for the first case history, before I move on to the second case history, is that at Kuala Lumpur limestone granite interface, so we encountered limestone floaters with regular thickness. So again, the message is very simple. It's very important to have adequate rock coring depth during soil or ground investigation works. And you only can do that if you are looking for it. See, just to recap, for example, if you don't look into it, you may be thinking that, all right, I terminate my borehole here, and you design your pile as limestone. So it can be very dangerous because ultimately, certain situation, let's say during construction, you actually encounter this while you're doing the bore pile, you puncture through it, then you have a lot of question marks. So these are the important things that you must look out for. So the bore pile foundation system was selected to socket into granite bedrock, and the instrumented test results match well with the assumed design parameters. And one important message is that it only matches well when you use it in conjunction with the adjusted rock socket length based on site obtained point load index strength, which I think is a useful tool to adjust the rock socket based on the degree of weathering or strength of the granite rock encountered. Okay, for my second case history, it's slightly different. Just now was on the limestone granite. this is on granite and Kenny Hill interface zone. So this particular site is not too far from Madrid. From the again from the geological map, the site locations indicate that it's near to the granite Kenny Hill formation interface zone. In fact, not too far from the limestone as well. But in this case, from the SI, we didn't encounter any limestone. So this a view of the site. Basically, the site, the highest ground is about 71 meters. Very interesting. I mean, again, some of my geologist colleagues will tell me that sometimes from the landform, you will be able to guess that perhaps there are something more that meets the eye, because the highest ground level is consistently on the right-hand side of this particular site. Highest about 71. The lowest level, RL 50, is on the left-hand side of the site. Of course, this particular site, we have excavation, and the final excavation level is about 37.5. So we have 30 over meters of excavation at the highest point. So again, from the SI, initially you can see, of course, the number of boreholes are less. We have maybe about total 15 numbers of boreholes. In fact, the first few rounds, only 3 numbers of borehole when the client is carrying out a feasibility studies. And luckily enough, I would say luckily, when we do the first 3 boreholes or so, it's only 1, 2, and 3. And we already managed to see that there's very obvious differences in terms of the ground conditions within the same site. And then when we carry out additional boreholes, 12 numbers, this is still fairly limited information. It just further confirms that there's a very distinct difference in terms of ground properties between the left and the right-hand side of the site. I mean, roughly we just demarcate it as such at that point in time. Okay, what we meant by that, you can see from here, this again, these are some of the typical borelocks that I'm showing you here between the granite zone and the Kenny Hill zone. You can see from here, for the granite area, in fact, some of the boreholes we encountered granite, but the rest actually, despite going to the depth of close to 60, 70 meters, we have not encountered any granite, but it's a completely decomposed granite, very high SPTN values. Whereas for the Kenny Hill area, you can see, of course, the main difference is that the hard layer is very shallow, and then we encountered different type of materials. We have sandstone, we have applied, we have, of course, weathered rock with SPTN more than 200. I'll show you a more close-up view with 2 typical borehole information, just to again illustrate the differences. You can see from the engineering point of view that the things that we have to tackle is that in granite area, the hard layer encountered, when we say hard layer, we define it as SPTN more than 50, because that is suitable founding layers and where the pile capacity derives the most capacity. That means the most efficient layer to derive the pile capacity. The hard layer ranges from 28 meters to 36 meters below ground level. All right. Whereas you look at the Kenny Hill area, the hard layer is very shallow. Basically, some of them is immediately from the existing ground level, 1.5 meter below ground level, you already encounter the hard layer, SPTN more than 50, and most of it actually more than 100, 200, etc. And even the others is only about 5 meters below ground. So the hard layer is very shallow, and you have very strong materials consistently throughout. Whereas at granite, you can see that you have soil before encountering completely decomposed granite. And I believe if you go deeper, you encounter the granite bedrock. So, and when we interpret the weathered granite rock level, of course, it's much deeper. It's about 13 meters below ground level for the granite zone, whereas for Kenny Hill, it's much higher. See, the difference is more than 40 meters in terms of difference in the interpreted weathered rock level. So, For the detailed design of this particular project, having established that we knew there are two distinct geological formations at this particular site, you can see I've color-coded basically those red color boreholes. The characteristics in terms of the profile, the soil profile, is closer towards the granite. We term it the granite site. Whereas the blue color is like what I've shared earlier, the Kenny Hill site. And of course, in between that, the interface zone, we have behavior which is a mixture of both granite and Kenny Hill. What I meant by that, you can see from here, this is at the interface zone. So you can see the what I mean by interface zone is that you have some soil layer go down. Then the hard layer, in fact, is deeper. Immediately next to it, you can see that this is Kenny Hill zone. Again, the hard layer is very shallow. In this case, at the interface zone, the hard layer is deeper. But the moment we encounter hard layer, then it exhibits some of the characteristics quite similar to what we encounter in the Kenny Hill zone, that you have a very good zone of materials which are with SPTN more than 200 before encountering granite in this particular zone. So here we have to devise a certain approach in terms of how we design the foundation and how to differentiate between at the Kenny Hill zone and at the granite area. So just to share some of site photos, of course, we have some diaphragm wall that we have constructed for the basement excavation. This site utilizes temporary ground anchors. These are the ground anchors being used in the construction of the works. Some of the wall required buttress to control the deflection. This one is exposed the diaphragm wall with temporary ground anchors with buttress as well. A view of some of the reinforcement cage of the ball pile. While we're doing the works, you can see typical construction site, a good site to to capture when everything is going to plan. Some of the temporary steel struts for the excavation works, and look, when we look, and again, as I said earlier, having know the characteristics that we know there's challenges, but the main task for us as the engineer for this project is how to design the piles. We have to balance between safety and also cost effectiveness. So in this particular site, of course, we are using ball piles again because this is a high rise, and of course the ground condition and because of the basement necessitates the use of ball piles. These are the sizes that we have used, from 750 to 2.5 meter diameter. And we have, again, one of the useful tools that we have is we carry out 3 numbers of preliminary test pile. You can see from here why we have 3 numbers. Obviously, for preliminary test pile, 1 is mainly to study the behavior of the ball pile in Kenny Hill formation, 1.2 meter diameter. We have to debond it because when we do the test pile, it's at the original ground level, but the layer which we're interested in is actually after the excavation levels. That's why we have to debond it 16 meter to correspond to the excavation level. For PTP2, it's mainly for the soil, the good soil in the granite area. You can see here the pile here is deeper because if you recall some of the boreholes that I've shown earlier, some of the piles can be quite deep, and yet we don't encounter any bedrock. So this is to test those areas. That means, let's say we go deep enough, and then we rely on the soil. Here we only have 0.5 meter of rock based on actual condition. Whereas for test pile 3 is the area where the granite rock is encountered at a shallower depth. So we have a 5.7 meter of rock socket. So in this case, you can see here for the cartilage, I think this is the practical highest level that we can do for 1.2 meter diameter. This is very high. At the point in time, it looks kind of scary as well, and a lot of work by the contractor, in fact, to stack this up. these are all the instruments we place on the bore pile to measure the mobilized friction on the piles. If you look at the results for preliminary test pile number 1, I mentioned earlier we debond it. Why we need to debond it? Because you see, the nearest borehole around this area, in fact, we have a lot of soil material here, but once we excavate down, this is the level which we do the test pile. The basement actually is this deep. So the behavior that we're interested in is within this area. That's why we want to debond it and test the soil materials that are relevant to our actual application. So the result shows this kind of information. Let me just give you a quick recap. Of course, this particular in Kenny Hill formation, we mainly design it as a bore pile in soil with a certain fixed length. So that is warranted. If you can see from here, despite different SPTN more than 400 in fact for that material, that area, you can see the friction ranges from about 340 to about 500. Some of them, this one very low, I think it's disturbed because it's close to the bonded area. And end bearing, you can see because of the Kenny Hill material, I think one thing that I've always observed for Kenny Hill material, the slick durability is very low. That means upon contact with water, it tends to lose the strength quite rapidly for Kenny Hill material. So you can see here, especially when you compare with the granite earlier, you can see the end bearing is quite low that has been mobilized, talking about 400 something only. So from the result, you can see that the friction in the soil ranges from about 150 to 500 kPa, and for the sedimentary rock, the base bearing capacity is only about 400 kPa. So what we do is that there's a lot of value in terms of carrying out the prelim test pile. You can see that these are on the left column here. Sorry, all right, there's some interference. Okay, so you can see from here, the original design parameter is about 2N, friction is about 250, and the rock we assume 700. Then of course we adjust this again. But after the test pile, we actually remain it for the soil 2N, but for the limit of the soil friction, from the result, we can upgrade it to 350. And if you do encounter very good rock, more than 3 megapascal, we can actually use higher, but this is not encountered. So, in fact, based on the piling record, equal rock socket length based on volume index hard to achieve because most of the time, the materials that we took out here are actually very fractured, so that there's no meaningful result from strength. So at the end of the day, the design is based on a fixed length. So even based on that, from the prelim test pile result, we managed to reduce the pile length by about 30%. End bearing is ignored due to the following reason, because the effect is not significant. Because let's say, for example, 1.2 meter diameter only reduce 0.323 meter of pile length. And we know that Kenny Hill material softens upon contact with water. So again, these are the observations from the test pile results. Whereas for the other two prelim test pile, again, I mentioned earlier, mainly we are testing in granite layer. We have very good materials at certain depth. You see, this is our interpreted design value, N15, 32, 120. We have some 300, 500, etc. And then we have a little bit of a rock socket. Total pile length here is quite deep, about 65.4 meter. And from the result, you can see that these are typical results. I won't go through too much into here. Later on, I'll summarize in the table. So you can see again from the soil, you can see that the frictional resistance is about 200 in weathered granite. So similarly, below it, I'll go through quickly here, but one thing you can observe is that, of course, in granite, the base resistance is much higher, in this case, 11,000. So in summary, the correlation for friction to soil ranges from 1 to 7. And the limit for the soil resistance is about 100 to 180 kPa. Again, you can see there's a big, in terms of numbers, there's an obvious difference between this soil material and the canyon formation. And in this case, we cannot verify the rock friction, but we know the end bearing is about 11,000. Whereas for the other test pile, BP2000, we purposely socket more into rock. We want to find out more about the behavior of the granite rock. Again, these are some of the typical results. I won't go through too much into it. I will just summarize it in the table shortly. So you can see the rock friction, of course, is higher. Even IS only about 1, we get about 1,100. So lower IS, of course, we get lower, about 500. For soil, we get about, again, about 40, depends on the SPTN value, to as high as about 180. So end bearing, quite similar, we get about 11,000. So friction, for IS more than 3, we get 1,500. Okay, you can see there's a clear correlation with the index strength, or IS. Again, as a quick summary, the friction ranges from 1 to 5 times of SPTN, and the limit of the soil friction ranges from 100 to 180 kPa. Whereas in granite bedrock, you can see the friction ranges from 500 to 1,500 kPa, depending on the point of strength index values that we have obtained. And the limit of the end bearing is about 11,000, similar to the earlier test pile results. So, but if you look into the test pile results, despite you can see the uncertainties with the performance of the end bearing. This is very important for engineers. Normally, we design a building to make sure the settlement does not exceed 12.5 mm for a single pile. You can see from here that even for 1,800 pile, it can mobilize 11,000, but at a settlement of close to 80 mm. Whereas you see the other pile, it seems that it can mobilize at a very small magnitude. 5 mm, you could mobilize 11,000. So this shows again that I mentioned about the uncertainties of the workmanship. That's why we have to make a judgment. Even though theoretically it can go very high, we have to limit it because to cater for the difference in workmanship. So in summary, for this, for the design parameters, we maintain for soil 2N. The limit of the soil friction, we also maintain it 150. We can see from test result, it can go slightly higher, but I think 150 is appropriate. And then for the rock friction, we can adjust it. You see, maximum 1,500, but based on the IS value, we can actually adjust it. Instead of downgrading to 0.6 or 900, we can use higher, 1,200, 900, and 450 based on the prelim test pile results. And end bearing, in fact, we can increase it based on the results again. From 3,000, we increase to 6,000. There's a reduction of pile length in rock of about 30%, which is quite significant. So in summary, you can see the value of prelim test pile is that if you look at the original design prior to prelim test pile, the pile length is about 24 meters. I mean, for a typical case. Then we optimize it to 17.5. There's a reduction of 6.5 meter in pile length, or 27% of the overall pile length, which is quite significant. In the granite zone, for the 6.4 and 3 meters, now we reduce the rock socket to 2.1 meter, 0.9 meter. There's a 30% reduction in length in rock. The cost for coring in rock is far more than boring in soil. That's why reduction in the, despite only 0.9 meter, actually the cost effect is very significant for more pile in granite. And so you see, for construction, these are some of the approach that we communicate to the contractor. We have to give them different scenario in canyon hill formation. If no rock is encountered, we tell them that for different pile size, these are the pile length required, the maximum pile length. But there are scenarios where maybe you do encounter rock. You have IS more than 3 megapascal. Then we have to give a scenario. If rock is encountered at what depth, then they can adjust the pile accordingly based on this table. So for granite, again, similarly, we will tell them if no rock is encountered, what will be the maximum length. But if you encountered a rock at what depth, they can adjust it accordingly with the corresponding rock socket. So for the interface zone, you can see that again, we have to cater for it. We have to design the soil based on granite area. You can see the length is very similar. What is the length? But then again, the depth will be deeper. If rock is encountered 25 meters, we know from the SI, then how much would be the rock socket? So the rock socket here, interface zone, we cannot assume that it's granite. We have to assume it based on a lower value based on sedimentary rock. That's why the soil is a combination of soil is based on granite, lower strength, but the rock is based on Kenny Hill type of rock, sedimentary rock, which require longer rock socket. This is how we tackle the interface zone. In fact, if you have very long pile, in this case, because of the limitation of the machinery, we have to adjust it accordingly, where we have to add more piles if for big diameter piles, because there's no way the contractor can form very deep piles. So I'm near the end of my presentation. As I mentioned earlier, my approach is that I want to share some of the observation on interface zone, and I'm sharing with you how engineer tackles this particular issue. But my message is very simple. Only one simple but often overlooked message is that the SI is very important, especially when we know that the soil condition, the geological and geotechnical condition at the site there is complicated. SI is, compared to the overall construction cost, actually is a very small portion of it. I don't think it makes sense to save on SI. And again, of course, there's huge benefits in terms of carrying out the instrumental test pile, in terms of verifying the engineering assumptions on the design of the piles. So I like this particular drawings in one of publication by ICE, is that they said that you pay for soil investigation whether you carry out or not. In fact, you eventually pay more without a soil investigation. Of course, they are making fun of the problem faced by this famous Leaning Tower of Pisa. Okay. So in fact, the ICE, they published this on a report by the Ground Board, the Institution of Civil Engineers of UK, simply titled Inadequate Site Investigation. One of the principal conclusions are, two of the principal conclusions are delay and escalating construction costs, and mainly due to inadequate site investigation. The consequences of inadequate SI is not only severe during design and construction stage, but can be even more serious for full life costing. That means, in other words, for example, the Leaning Tower of Pisa, your foundation starts to have problem, then only you try to rectify it. You know, the maintenance, the cost of underpinning, of rectifying the initial problem, in fact, can be even more serious in the full life cycle of the particular building construction. So with that, I thank you for your attention, and I'll be happy to discuss if there's any opinions that you want to share with me today. Thank you very much.
Yeah, thank you, Engineer Chow. A very interesting presentation, case studies. Okay, let me open to the floor for questions first. I think our good friend is Robin Liao. He's our resident guy who.
Hello, Professor yes. Tan.
He's our resident guy who asks a lot of questions. Okay, you can start the ball rolling, Robin.
Thank you very much, Professor. Okay. Yes, Engineer Chow.
Yes.
Most interesting, what I call this presentation, and Professor Tan also. What I call this, not to say surprise, but he actually written a paper on what I call this interface, granite limestone interface, and at interface there's a trench, as Engineer Chow mentioned. So very interesting. Number one, Engineer Chow mentioned, when we drill and if we hit a bedrock, for example, limestone, that doesn't mean that it's already a bedrock. It might be a limestone floater. So you have to drill deeper to confirm it. That's a very good conclusion.
Yep.
Yes. And number two, Engineer Chow, could you go to your case study 2? Case study 2 on this granite Kenny Hill.
Yep.
Granite Kenny Hill, and then this yes, okay. This part here, is this the interface?
This is at the interface. You see, this is we call it.
That's it. You see, it looks like the granite weathers more than the sandstone. That's one thing. But the interface is even deeper.
Yeah.
Now, this granite is Triassic. Kenny Hill is Carboniferous Permian. So the granite is younger. So this younger granite would contact between this interface here is a contact metamorphism. This should be quartzite. These are quartzite. So it looks like the quartzite weathers more than the granite. Same thing, if you go back to your case study 1, you have the granite and the limestone, what they call this?
Interface.
Interface. And that limestone interface, but it's not shown here. It's not shown here.
Yeah.
So just now I was wondering, whether these are cavities. But it appears that these are limestone floaters, it seems. Are these limestone floaters? So this part, why they are floating? So this part is actually these are scan. These are what they call this weathered scan. This has got to be scan. Weathered scan.
You mean which one you're talking about? We have scan encounter. You see, what we have.
Yes.
What we have
because at the bottom here, these are granite.
Yep.
This is limestone.
Yep.
So granite, limestone.
Yep.
So in between there must be scan.
Yep.
In between scan. So these are actually weathered scan.
You mean the below the limestone?
These are weathered scan material. It has got to be. These are weathered scan material. So the thing is, like Professor Tan paper just now, he was mentioning at the interface, granite limestone interface, there's a trench. Same thing here. This is granite limestone. Same thing just now, granite sandstone. There's also a trench. At the interface, there must be a trench. What I'm trying to say is that the contact metaphors material is is less resistant to weathering.
So that's why you said your
yes.
observation is you see there's a thicker layer of weathering at the interface zone, correct? Is that
yes.
What? Okay.
In this, and the scan is more weathered than the granite. Same thing just now. The quartzite is more weathered than the granite. So the contact metamorphic material is more weathered than the limestone, than the sandstone, the Kenny Hill sandstone, than the granite.
I see.
So that's my observation. That's interesting. I had thought scan material is very resistant. Same thing, the quartzite should be very resistant.
Yeah.
It doesn't. It's not.
That's why because Mr. Liao, Robin Liao, I mean, yes. As I mentioned earlier, I mean, on the geological behavior age, I think I leave it to the experts here. I mean, from my understanding is that normally when we test the scan material or the quartzite, normally the scan strength and the abrasiveness is much higher You see, that's why when we encounter skarn or quartzite, we are very worried. We talk about tunneling works. We're very worried that in fact it will wear out the tunnel boring teeth much faster. Boring teeth.
Yes.
That's why.
Yes.
That's why
Harder. It's
it's
hard.
supposed to be harder, but I don't.
It's
That's
supposed to be
why
harder. Yes.
I do not know
But-
why in this case.
Yes, it's supposed to be harder. But it weathers more. But in this case, it weathers more.
Yeah, I do not know. That's why I'm only presenting the
Yeah.
actual observations that I have. That's why
Yes.
I must admit I do not understand how the mechanism of all this that have resulted in such characteristics.
Yeah, very interesting.
Yeah.
Very interesting.
Maybe some of you may can initiate some further research and understand better why the information. I'll be happy to share my SI information, the lab test results, all those things. Then maybe somebody will be able to give a better story of how all this come about.
Yeah.
Thank you, Mr. Liao. I think
Yes. Thank you, Engineer Chow. Thank you, Professor Tan.
Yeah. Any more questions, Robin?
No more.
Okay.
Very interesting observation just now
Okay.
at the interface zone.
Yeah. Okay. Then we move on to other members of the audience. I like to call the audience to ask questions. We have some very senior guys, but they're keeping very quiet. Practicing engineering geologists. How about our senior Chen Shipei? You're there? SP Chen.
Tan Phong Gong, how are you? Long time.
Yes, good. Yeah. You're a very
good.
senior guy.
Yeah.
Mr. Chen was one of our ex-director general, GMG. Any questions from you?
Yeah,
This-
thank you very much, Dr.
Yeah.
Engineer Chow. Very
Yeah.
interesting, very interesting talk, and I enjoy very much. But it is a non-geological question actually. Whether we are engineers or we are mineral resource person, we always need to do site investigation work. And of course, being an engineer or geologist, we try our best to plan a program that can get the maximum information, and not for us to enable to contribute to the design or future development of the site. But very often we do not control the purse string. And then the client is the one that controls the purse string. That's how the engineer Chow was very lucky. He has an engineer client that allows him to drill 110 borehole at the site. But very often the resources available to us are very often, this is the first they want to cut for a project. They don't cut construction costs, but they always cut the investigation costs. So in the case where say, okay, to gather the information, I need to drill 50 boreholes, and the client said, no, based on what the first few walls, I think 25 is enough. How would you deal with such a case, Dr. Chow?
Yeah. I think this is a very real problem. I think that everybody, when we say we are in this industry, either as a geologist or engineer, I think it's a very real problem. I think especially when we are talking about some client, they review this, they thought it's a low-hanging fruit. They say that, oh, I'm doing a very good job for my company. You see, I managed to cut the engineer's budget for SI from 50 to 25. Initially, maybe the cost is 250,000. Now I managed to save the company 100,000. Okay, how we do this is I must say that it not necessarily will work every time, but some of the strategies that we have used before is we are lucky that we do have some projects, sometimes certain projects that suffer badly because of inadequate SI. You see, this client, that's how I mentioned that I'm lucky for this client, is that In fact, for the same company, this under different management, they were developing this particular condominium in Sunway area. So they have very limited boreholes. They're talking about 3, 4, 5 boreholes, and then they proceeded to start construction for the foundation using bore pile. And the design goes that every single piles need to be socketed into the limestone bedrock. So what happened is that while they are doing first half of the building, no problem, going as planned. Then suddenly, when they move towards the other side of their particular building, when they start drilling the bore pile, they drill deeper and deeper, 60, 70 meters, there's no rock. They did not encounter any limestone rock. So the engineering instruction is still the same. You have to socket in the rock because in Malaysia, most of the limestone on top, most of the time is ex-mining land, very loose sand materials or loose dump materials. So those capacity are useless to soil. So as they go deeper, they still cannot find rock. They say, hey, this one cannot go on anymore. Then they only decided to bring in SI machine and try to investigate. And they only found out that particular area maybe it's a remnant of previous mining activities. So after a certain area, there's a huge drop in terms of the bedrock level. Then they have a lot of problems. They have to recall tender. They have to repackage the foundation design, redesign everything. So my message is like this. Something like a doctor. When the client refuses to do so, we will show them actual nightmares when projects don't have enough SI. In a way, I will use the word, we have to show them the nightmare scenario and scare them off first. Like you see, when you showing children sometimes, you have to show them the scary part, then only they will follow your advice, you see. So that's one approach that we have used. As I said, sometimes it works, sometimes some of them still very stubborn. And another approach that we have used before is that, in fact, we tell them that you do not view SI as cost. You should look at it as investment. You see, if you invest 100,000, you reduce your foundation cost by 1 million very easily, because if you have one borehole, of course, the engineer have to design more conservatively. But you have invest more, extra 100,000, and that's why I also showed from the test pile result, more testing, I can reduce the design more efficient. That means you're investing extra 100,000 for a return of 1 million. So no way you can get this kind of 100,000 and 1 million investment. So some people, when they view from that point of view, they find that the money is worth spending. Okay, so these are some of the approach to view. But ultimately, some are so stubborn, we can't do much except we will highlight to them all the risks. This is another good approach from an engineering point of view. Now we have an approach called a risk register. That means we upfront we tell the client already, okay, if you don't do so, these are the risks. So eventually, when things don't go as planned or it's worse than what anticipated, we already highlighted to you earlier on. You cannot blame me anymore. Okay, I hope I've shared some insight. Of course, I unfortunately I must say that I do not have a solution that that be able to solve all the problem. My only hope is that more and more decision makers are from a technical background. More technocrats, then our life will be easier.
I think one of the problem, thank you very much for your sharing your experience. But one of the problem is that, okay, they said, okay, we don't have enough money, I cut you so much budget for the work. But ultimately, when the project encounters problem, like what you mentioned, they will go back to us, hey, you're a geotechnical engineer, why are you not seeing this problem?
Agree with you, Mr. Chen. That's why our thinking is, my experience is that one of the important thing is that we should not be afraid to share opposite opinion to the client. That means some may say that if I talk like that means I tell the client, if you don't do the SI now, these are your potential problem. Some may feel that, oh, it's not good to talk to the client like that. But I feel this is a very important because it's factual. And I really highlighted to him that because eventually, if things really goes wrong, at least you have pre-highlighted to the client. You don't shoulder the responsibility because most of the time the client may, when problem occur, he may say differently. He say, you should have told me at that time. These are the problem that I will encounter. If you have told me at that time, maybe you have told them verbally, not in written. He pretend to have forgotten it, and he can turn around and say that if you have told me, I would not have saved this kind of SI. You should have told me you are professional.
Exactly. Yeah.
Yeah.
So I think I fully agree. That's why I always advocate, if you cut my budget, these are the potential or possible consequences of doing this work. This may be the possible consequences. So to protect ourselves, especially in writing to the client. Yep. Thank you. Good job. Very good.
Chen. Thank you.
Yeah, there's a question on the chat. You want to read it?
I saw the question in the chat from Mr. I guess it's Mr. Leong or Mr. Mo. I'm not too sure the way he was. He said other than doing SI, will the geological mapping be cheaper compared to SI to map up the whole site? Where is the bedrock? I'm not too sure I get the question correctly because for my job, most of the time the bedrock, there's no outcrop for me to carry out the mapping other than through the drilling of SI. Of course, in our office, our team of geologists is very useful when there is outcrop or there's a study of the features of the ground. Normally, they already advise us that whether there are certain things that we should be careful of, you see. Just to give you an example, illustration just now, I'm not sure, Prof. Tan and all the experts here, maybe you correct me if I'm wrong, what do you mean by geological mapping? But just now, when in the beginning of this presentation, as I've said, in fact, some of my geologist colleagues already highlighted to me that they suspect unless the ground is disturbed by prior activities, they suspect that the ground conditions here will have a distinct differences based on the topography of the site because they observe, I mentioned earlier, very obvious that this area of the site, they have existing steep hill, the ground level is much higher on the right-hand side on the Canny Hill Formation. Whereas on the left-hand side, the ground is flatter and there's no features of hill over here. I mean, there's a very pronounced change in terms of the topography of the site between the Canny Hill and the Granite Formation. So, of course, our geologist counterpart also highlighted to us that we should be on the lookout for differences in terms of geological features at this particular site. So that's my comment.
Actually,
engineer.
Go ahead, Robin.
Sorry. Okay, Engineer Chow, you go to slide 41, please.
Slide 41. Okay.
This is 42.
41. All right.
Slide 40. Okay. Now, just now the question, geological mapping, SI. This is what geological mapping, doing geological mapping, this is what we get. We get this site, Kuala Lumpur limestone, this one granite, this one Canny Hill limestone. So this is geological mapping. But if you have to build anything on top of this site location, SI is a must. You cannot base on geological mapping like this. This is just it just show this is Kuala Lumpur limestone, this is granite, this is Canny Hill sandstone. You cannot base on this geological mapping to build anything. So if you go back slide 42.
Slide 42, all right.
Or slide 41. Slide 41. Slide 41. Slide 42. So if you want to build something, you have to do SI. SI is a must. You cannot base on the geological map.
I see.
Just my
Okay, that
comment.
thank you, Mr. Liao, Robin,
Yeah.
again.
Yeah.
Yeah, if that's what the the earlier
Mr. Mo,
question
Mr.
was,
Mo.
Mr. Mo, I think for my approach is that based on a geological map, it's a very macro over of the site. That means it gives us a good base
Yeah.
to plan our SI. That means we sort of have an idea what to look out for, because if you carry out SI in Kenny Hill Formation and you carry out SI in granite, in limestone, there are differences that you
Yes.
to look out for. Even the number of boreholes may be different. You see, like if you have a site that you are very sure is in granite formation, 100%, you don't need so extensive borehole. For instance, I mean, the client have the right just now to share what Mr. Chen say. I mean, a lot of boreholes is good, but only when it's necessary, not necessarily, just for the sake of carrying it out. So that's why the geological mapping has its use. But like what Mr. Robin Liao said, for engineering works, we still need SI for a detailed design of the foundation and all the geotechnical works. Thank you, Mr. Liao, for clarifying it.
Right, last call from the audience. We have a couple of minutes left.
I think there's
finish
another
at
question.
5:30.
Yeah,
Last question from the audience. Anybody
there's
else?
Sorry, Professor Tan, I saw a comment from Mr. Sheikh Hadi, Sheikh Abu Bakar. He said, just sharing his experience during SR drilling in KL limestone area, hit rock at the original borehole position around plus minus 20 meter, offset 1 meter from the borehole, we encountered bedrock. So let me see. Okay, wait. Encountered bedrock at plus minus 100 meter. Yeah, I think this one he just shared with us. I think again, I think a lot of here experienced people, if you're talking about Professor Tan, Robin and Mr. Chen, that's the thing about limestone. Some limestone are natural, but you have to be careful of the history of limestone in Malaysia as well. Many of them may be quarry mining area. So the natural feature itself also, you have possibility, that's how I showed the earlier paper, that the rock can have a drastic drop. Natural features can happen, and some can be man-made also, is possible as well. That means surrounding is all the original quarry hill. Then suddenly, as you move towards the middle of the old quarry, of course, the limestone may be very deep. So you have to be aware of all this and with your eyes open, and it should not be surprising. That's why in general rule of thumbs, boreholes tends to be much more in limestone area.
Okay, I just have a quick comment before we wrap up. Your coring of limestone floaters, how much, what's the cutoff you core off at 20 meter, 30 meter? How do you know when to stop, whether it's a floater or not?
When there's floater, I mean, in this particular case, okay, in totality, in summary, on average of all the piles that have been constructed at site, on average, actually, the extra limestone that we have core, if I'm not mistaken, is about 1 meter extra for each pile after we average it out for it. But the approach here is that we do not limit the limestone, and because we have enough SI, we are quite confident that, because we know that the scan on the granite is typically about 40 to 50 meter below existing ground level. That's why at the end of the day, what the contractor do is that we observe what are the materials when they core until 40 to 50 meter, and whether it reaches the granite layer. And I'm happy to say, because of enough SI information, this most of the time, I mean, in fact, all the piles is as per prediction. That means we have minimized the surprises to a bare minimum.
No. The question was your coring length. When do you know when to stop, whether to prove that it's a floater or it's not a floater. You know, your
Or
coring length of
for the
coring length
SI. For the
yeah,
SI, is it?
yeah, SI coring length to prove or disprove a floater lah.
Or no?
Used to be
For this-
like, I don't know, used to be 5 meter. Now yours is 20 meter, is it? Coring length.
Yeah. Okay, Prof Tan, just to elaborate, for my normal projects in limestone, not in interface area, for normal limestone, usually we just based on statistical and of course some of the publication that we refer to, right? We based on 10 meter, and I think it has served us quite well, 10 meter into limestone, that to prove sufficiently that that is bedrock and not floaters. Seldom I've encountered floater that is thicker than 10 meters. But that's why I for this particular site today here, I highlight is that in interface zone, it may not be the situation. In this case, earlier I've shared earlier, some of the floaters in fact is up to 20 meter. I mean, not all single point, but you see we have at least 2 boreholes that is 20 meter. But in this case, we do not stop even up to 20 meter because we have enough SI information to know that granite bedrock will be encountered somewhere around 40 to 50 meter below ground. That's why when we do it true enough, after certain depth, we encounter the weathered material. According to Robin, it should be weathered scan. I mean, I don't know, but the material is
It should be weathered scan.
Yeah. So you see, after that, despite 20 meters, we have soil, then we go back to scan and then granite. So in this case, for this site, we do not stop it. We do not define it either it's 20 meter or not. We actually go through until at least 40 to 50 meter.
Okay, I think our time is up. So I like to thank the speaker, Engineer Chow, for taking your time to give us a very interesting